Okay. Good evening from me as well. Thank you, Professor Klemesh, for the introduction. I would like to present my viewpoints and what my concerns are and issues I would like to see discussed and to draw some strategies for the future. For me, the process integration field and the total site integration have reached a level of maturity where we need to introduce certain clarifications and try to devise unified approaches as much as possible without imposing areas, and this includes total site concept. And it has several dimensions. Firstly, as it's become apparent, the total site idea moved from a purely industrial context to residential and spatial planning context. And further, we can talk about increasing the geographical spread and regional development about Professor Radoslavske he will discuss. We have more and more application areas. Besides heat integration at the site level, we start to talk about water integration. We can start discussing also other types of utilities and resources. Total site has started initially as just thermodynamic analysis and targeting. And step by step it's developed to tackle more task types, including system design, supply chain optimization, and so on. In addition to this, because a large number of researchers have dealt with these issues, everyone within even same application area have developed their own contexts, their own concepts, which sometimes differ from each other. And in many cases, I find it useful that if we are to use efficient tools, we need some kind of unification of the concepts, or at least a mapping. This is what we've made several years ago, a couple of years ago, with Professors Kravania and Klemesh, and this review paper shows really the diversity of the approaches and applications. I'm risking to repeat some slides, but this is important for you to point out there are many applications. First is the move to geographical context, then further development even within industrial context. There are other issues, more details and important concepts tackled. And all these have departed from the original total site integration concept, but they're not really linked to each other very well. Town and spatial planning. And again, not just research. Well, these are the efforts. We have a number of books. It's not just the research efforts. Books are the excellent medium of taking a breath, look back, sort out, and systematize things. So the books, for me, are part of the solution to this issue. But probably more frequent discussions, common projects would be another part of it. So that's for me as an introduction.
Thank you, Petar. And the next introductory speech would come from Zdravko Kravanjo.
Thank you for the introduction. Good evening, ladies and gentlemen. First, I would like to thank the organizer to invite me to be part of this panelist. Actually, I put the title to this discussion as a question, and it is it worth to pursue the synthesis and retrofit of large-scale heat exchanger networks, which we found at total site synthesis by mathematical programming approach. You know, mathematical programming approach is actually, I won't say a new emerging area. It is already mature, but it is more and more used. The scope of heat integration is actually to perform it at the level of equipment, processes, and between processes. And the question is how to perform it simultaneously. Because if we can perform it simultaneously, then we can gain some additional benefit, because we are exploring additional interactions between the system. And the optimization is nothing else than just exploring interactions between the system. So far, we have two approaches, or three approaches. The first one, pinch analysis, mainly governed by graphics, and then mathematical programming. Mathematical programming, as you see, you have a model described by equality and inequality constraints, and then you have some criteria to maximize or minimize, and you have continuous variables and discrete variables for continuous and discrete decisions. The model should have some positive number of degrees of freedom, and using those degrees of freedom, we would like to find out the best synergy within the system so that we maximize, for example, yearly profit or net present value or something like that. There are some very important creative principles embedded in the mathematical programming. The first one is optimality. Whatever you get is already optimal, and that has some competitive advantage. Another thing is we can put whatever constraints in our model, and at the solution point, all those constraints should be satisfied. So we get a feasible solution. And then we can also merge different models together in order to perform simultaneous optimization and synthesis, and this gives us integrality of the solution. By using mathematical programming, a new knowledge can be developed, also some new innovative solutions. But what is also important is that by study of solution, we can get new insights. One typical such an example is that while performing simultaneous heat integration and process optimization, it is not only that we are saving the usage of external utility, but when we have recycles, we are saving also raw material. And when raw materials are expensive, then in that case, we save much more than just by utilities. The question is, can we solve industrial problems at very large scale by using mathematical programming approach? We can say that this approach is becoming mature tool. Computational speed and also the efficiency of algorithms for optimization have been improved over the last decade by several orders of magnitude. So this is a good point, and we can explore it. But still, industrial processes and problems, especially like refineries, total site. There are heat exchanger networks with several hundreds of hot and cold streams. They are performing operations under dynamic conditions and can be handled that problems by using mathematical programming, and not only to obtain the solution, but solutions that are even close to global optimality. That's the real challenge. If we look at the level of the process scheme, first what we have to do is to draw the so-called superstructure, where we put all possible combinations. For example, for 2 hot streams and 2 cold streams in several stages, we can have several alternative matches, and then the role of optimization and the synthesis is to find out which match to choose, how much heat has to be performed, heat transfer had to be performed in the match, and so on. You can then imagine that if we have a large number of hot and cold streams and then also large number of stages, then we have a lot of alternative matches. And just to give you an idea, for real case industrial case study, we have like 4,000 or so matches. And combinatorics of that problem is 10 up to 1,300. So these are kind of problems that we are dealing with, and by our mind we cannot comprehend all those possibilities behind, but we are lucky to have tools and knowledge, and if we can explore that tool and knowledge to get solution, then we are winners. The problem becomes even more complicated if we would like to find out not only which match to use, but also what type of heat exchanger should be put in that match. And then the problem becomes even more complicated if we would like to do the retrofit, because by doing the retrofit we have to also consider the existing heat exchanger possibility to use, to relocate, and so on. So the number of possible combinations are really exploding, not only increasing. So far, several models have been developed. First model used sequential strategy approach, which is easier, and then after some simultaneous. This what you can see is simple. It looks actually complex, but it is simple superstructure because it is only 4 processes. For each process has 2 cold and 2 hot streams, and for the purpose of total site heat integration, when sequential strategy is used, that means that heat integration is first performed within each process, and then hot ends of processes are then used to heat up intermediate utilities, which are then used to heat up cold ends of cold process streams. Situation become much more complicated when simultaneous strategy is employed, because now we do not have only hot and cold ends of hot and cold streams, but each hot stream is not only connected within the process, but also outside the process, either directly or via intermediate utility. And if we have several intermediate utility options, then we of course have many more options, and not to mention that it is worth also to perform simultaneous pipeline optimization and design. But what we find out is that just by using simultaneous approach, even if we had to merge several models together, we obtain for in one case study, 64% better result. Performing pressure level optimization for intermediate utility, another 63, and then when we forecast future utility prices, another 18. So that means it is worth to pursue simultaneous approach. However, there are several drawbacks. Complexity of models are really very high. A lot of non-convexity, so we got stuck in local optimal solutions. Exploding combinatorics. I have to say that even with the best computers, the best professional codes for mixed integer linear or non-linear programming, it may take several hours to get a single solution. So far, only small problems have been solved, and the user should be an expert for mathematical programming. However, there are some very powerful advantages. The appropriate trade-off between utility and investment can be obtained. Once the model is obtained, and model should be developed as data independent, then it can be reused for any other application. Only data has to be changed. Different constraints can be imposed, like forbidden or required matches, which is very important for industry. And since we can perform multi-period modeling, then we can also obtain, at the end, flexible design considering dynamic operational condition. So the challenge here is, can we improve our approach by some other method? And the other method is actually combined pinch technology mathematical programming approach, or let's say mathematical approach that is based on insights from pinch technology. This is again the same picture as Professor Clemens showed you before. I would just like to stress that just by using psychical insights from pinch technology, that can be used to narrowing the optimization search space to give the exact borders. Then what is also important is that global optimal target can be indicated based on thermodynamics, and that can also guide the non-convex problem optimization closer to global optimal solution. Then graphic is very important. Industrial people don't believe in equation and numbers, but they would like to have they would like to have results in graphic. And this is the methodology that has been recently developed. First is data acquisition for dynamic operation condition. Then based on that, there's targeting, just to see what are potentials for improvement. And then based on insights from pinch technology, using mathematical programming, the idea is to identify the most profitable modifications where the trade-off between investment and energy is obtained. And then the next step is verification of those modifications by engineers in companies. And then we do these several loops. In our case, we do 4 loops, and by doing that, at the end, we got the final feasible retrofitted heat exchanger network modifications, for which we perform more detailed synthesis, and then out of those numerical solutions, then we perform a graphical presentation of the solution. I would just like to show you, here I would like to acknowledge the European project called HENS, and we actually developed this methodology within this EU project, and we actually perform it on the industrial case study problem. So this is what we get for different scenarios, the targeting step for total site. This is an example of table that was sent to engineer to the company to check all those profitable modification. This is the example of Gantt chart for 15 modification, and this is then the final, an example of final process scheme where those modifications are drawn, and this is the result that a company needed at the end. So the conclusion would be, yes, it is worth to pursue the synthesis and the retrofit of large-scale total sites by mathematical programming, but not just by mathematical programming, but the programming that is based on insights from pinch technology. By that, I would like to thank you.
Thank you, Zdravko. And the next speaker is Dr. Sharifah Alvi, and he will talk from the little bit other perspective.
Okay, very good evening, everyone. So I can see everyone is quite sleepy. All right, so I'm going to talk about something almost similar, but I would like to go not only on energy, but all the resource supply chain management. Okay, before this, it's quite easy if we start from industry, okay? Because from industry, we produce products. And industry, as we know, consumes lots of resources such as fuel, electricity, water, and raw material. And at the same time, it produces lots of emissions, wastewater, and various types of waste, waste heat, waste gas, biomass, waste, and many others. Yeah? So what we want to do is, if possible, we want to reduce the use of the resources, fuel, electricity, and so on. At the same time, we want to reduce the waste. Yeah? So the main question that we would like to address in this session is basically how to minimize the resource utilization and at the same time how to generate less waste. So one of the several ways that we can do is not only to look at the recovery part, but inside our center, we are also looking at the whole resource management hierarchy perspective. So what we are looking at in our center is, aside from heat recovery, water recovery, CO2 recovery, and so on, we also think about how to do source and demand manipulation. You might be wondering, if you look at this hierarchy, if you are familiar with the waste management hierarchy, typically elimination is first. And then this is followed by reduction, reuse, and so on. But you might be wondering why we are putting recovery first in this hierarchy. Yeah? The reason is because if you look, if you don't do recovery first in the whole analysis, you don't know if when you are eliminating a source or demand, that source or demand can actually reduce your fresh resource consumption and your reduce your waste generation. For a simple example is, let's say that demand can actually accept a source, but you are eliminating that demand. So this source cannot be consumed by the demand anymore, so it will become something like a waste. So that is the reason when you want to do a resource recovery solution, you have to do recovery first, followed by the addition, looking at the source and demand manipulation, and then looking at what are the possible ways of outsourcing, taking things from outside like rainwater harvesting, the one that Prof. Zainuddin has presented in his lecture. And then you should also think, okay, if I cannot do reuse or recovery directly, the next thing is how can I upgrade my reuse? Yeah, so let's say you have a contaminated wastewater, so you cannot reuse it directly. So the next thing that you have to ask yourself is it possible for me to treat it partially so that the quality is better now, and from that way you can reuse it. The same can be applied for energy. If you have low waste energy, you can use a heat pump, upgrade the heat, and then after that you can use it for a higher quality heat sources. So that is all about upgrading. And finally, if you cannot do recovery, maximize recovery, you cannot manipulate your source and demand, you cannot take out source like rainwater harvesting, you cannot upgrade your heat, the final one is you try to use your fresh resources. Okay. All right, inside our center, I'm from Process System Engineering Center from University Technology Malaysia. We do the whole resource recovery solution. And not only the resource recovery solution, as I mentioned, we also look at source and demand manipulation, upgrading, and so on. And that is talking about single site, yeah? But in truth is, sometimes you cannot fully utilize everything inside one industry, so you might still have excess waste. So that excess waste you can actually share with other industries, which create the industrial symbiosis concept, right? So if it's not possible to fully utilize in single industry, the next step is to think about exchanging with others. So this is the interplant or total site resource recovery concept. Yeah? So first thing, and if possible, we don't want to go so far away. If you have one industrial site, it's better to integrate within that industrial site instead of, for example, like Prof. Giri has mentioned, getting a transportation and transporting some sources to other locations. So if possible, we want to maximize something within an industrial site. But that is only talking about demand side management. Sometimes after you have tried to utilize everything, maximize all recovery and so on, you still need some supply or some resources. You still need some. You cannot eliminate completely resources. So from here, we actually need the supply side management. Supply side management is like, for example, hybrid power system using renewable energy. So instead of using coal for you to get heat or electricity, you can substitute it with renewable energy and so on. So supply side management, we are also doing this. We have the power pinch analysis, we have water minimization solutions and so on. So when you are trying to minimize emissions and resources, you should actually look not only from the demand side management, but also the supply side management. And not to forget, sometimes after you have already tried to change to renewable energy, but sometimes since it's not economical yet, you might not be able to completely 100% change to a renewable energy system. So you might still have some emissions. So the next thing that you have to think is the end-of-pipe management. End-of-pipe management is about reducing the environmental impact. So let's say I still have to generate some wastewater, I still have some emissions, CO2 and so on. So what are the possible end-of-pipe management solutions that you can do so that you can reduce your environmental impact of your whole site system? So the thing that I would like to propose is, typically now, many people are working only in one area. Yes, some people are more focused on demand-side management, some are working on end-of-pipe management solutions, some on the supply-side management. But actually, all these three management are integrated. Yeah? So for example, if you reduce demand, you actually reduce also your power plant size, yeah? You also reduce your emission, and then you build smaller wastewater treatment plant and so on. So actually these three management systems should be integrated together, should be considered as a whole, and if you have many technologies as the things that most of you have presented in this SDEWES conference, we want to know, okay, we have all these available technologies nowadays, so which one is the best? Which one should we apply for each one? And how do we do it systematically? Right? So for me, the future challenge is how can we model the interaction of the whole resource management supply chain, considering demand side, supply side, and end-of-pipe management system. And most importantly, after we have done the modeling using whatever pinch or mathematical modeling approach, the next thing that we should think of is how to make it happen. It should not stop only as an academia exercise. In my opinion, it's good. We're academicians. Yeah, most of us write journals. But the next thing is, how do we make it happen? How do we reach the industries? How do we reach the politicians? How do we reach investors, businessmen, and so on? So maybe the next question after we have done all this screening, all these systematic tools, we have to think about knowledge transfer. Okay, if you guys notice, when we publish in journals, actually policymakers, they don't read journals. Yeah, because the journals need to be subscribed by Elsevier, for example, and then it's so expensive. Many people, engineers and so on, they don't subscribe to Elsevier and so on. So the problem is, even if we publish so much in all the various angles of management, sometimes they don't read it because even if they read it, they don't understand because it's too complex. So what we need is actually someone who can help to make a simple guideline for industrial makers, for example, and then make it simple, okay, how to make systematic screening approach, integrating all the various technologies that people have proposed, and then make sure it's published maybe in an open access publication and not something like closed access publication. And of course, the next thing is knowledge transfer. We have to go outside there, talk to the engineers and so on, transfer how to do it practically to them. And then the last thing is implementation. Yeah, we have to really implement the method, test it on a real case studies, industrial sites, and so on. So one of the things that I would like to also highlight is how can we reach the users? What are the business models so that businessmen will want to implement all our techniques? And what can we do on education, training, awareness, and so on? So that's all from me. Thank you very much.
Thank you. And Michal Narodoslavsky will come with his view from a little bit different angle.
Yeah, I think so.
That's your fast one.
Well, before all this starts, I just want to start with an old saying about Austria. And I was tempted to that by Jerzy slide about the martial arts. Huh? So fighting against each other, mathematical programming against everything else, and pinch and so whatsoever. There's a saying, tu felix Austria nube, which means, you happy Austria, marry. So the Austrian-Hungarian Empire was married and not taken by war. And that's what I want to tell you, in a way. I mean, we will need all these approaches in, I would say, a concise and a new structured way. And I'm starting with that because my problem is, of course, biogenic resources. So I hope I can manage that thing here. Nope, that was the wrong one. Okay? Okay. So the first thing that I want to highlight is if we talk about biogenic resources, and if we look at them from a service point of view, what you see here is that the services that come from biogenic resources are quite manifold. And now So you have here social services like nutrition. I mean, nutrition is based on biogenic resources, and we can't get away from that. It's jobs in regions, it's social stability in regions. Then we have other services, economic services, and I have had these lists here, and on the right-hand side, what you see is if there is competition from other resources. And you see here in the social side, there is no other resource that can actually supply that. In the economic field, with the sole exception of feedstocks for conventional bio-based industries like pulp and paper, we have lots of contenders who could also do the job, like transport fuel, like stability of energy distribution grids, and so on and so forth. There are other ways to do it outside the realm of biogenic resources. And down here, you have the environmental issues and the environmental services. And you see here, reduction of greenhouse gas emissions. Well, there are many contenders. many other renewable resources that we could utilize. But there is no way to actually use any other resource to preserve our soil fertility, to preserve our water qualities and things like that. So we have to really concentrate, if we are using bioresources, on a rational utilization of this particular sort of resources. Okay, so what we have now, what we usually have is a gate-to-gate approach, and that is process industry. I mean, in goes raw materials, whatever they are. We have the process that converts them into products. On the other hand, if we talk about what goes in the intellectual, from the intellectual way, we have, of course, our process engineering, our unit operations, whatever you have, even process integration. And what goes out is construction and operation of our industrial plants. That's what we do, or that's what we have done for the last 50, 60 years. That will not suffice if we talk about bioresources. The gate-to-gate approach is just too narrow. And therefore, what we're going to do is to have a new approach, which is a kind of total site approach. Here, we have a new, I would say, a total site, which could be a region in this case. And what we have going in are resources, and here resources are not the raw materials. Resources are land, are fertile, are water sources, things like that, basic resources. And they might be converted into raw materials by agriculture, forestry, whatever, that we still have in this inner process that is still there. We still have process industry in there. But out goes, and that is also important, innovative services, solutions for service provision. We don't need products. We don't need heating oil. What we need are warm houses. We don't need transportation fuel. We need something that supplies us with mobility and connectivity and all that. So we need services. And that is a complete new approach and a complete new look at what we actually have as a total site. In goes, in this case, resource management. Sharifa has told about that. Yes, we need resource management. Supply chain management also means that we look at what is happening out there with the basic resources like water and soil and so on and so forth. We need transport systems to get from these resources our raw materials into our processes. We need energy systems, not energy as such, energy systems. We need distribution grids that bring energy to our processes. On the other hand, in goes, on the product side, the distribution, the use phase, and the whole thing actually in terms of structures. So what we are talking is not only processes, but we are talking about full structures of process systems. And there, of course, go in other things in terms of the intellectual side. We need systems engineering, and what I would say is that process engineering is a very good starting point. We have developed a lot of the methodologies that we need for solving also this larger process or this larger site problem. It goes in life cycle analysis to actually have a hold on what actually happens. Supply chain management over the whole picture that we have here and all that stuff. So that is an enlargement of the process concept. And this enlargement can be based on a lot of what we have in our, I would say, arsenal from process industry. And out goes, of course, minimized ecological pressure of the whole system, not of single processes, of the structure that is within that, and maximized social benefit. So we are also optimizing different things here. So that is my enlarged process concept that we need to integrate. And if we talk about bioresources, I mean, there are rules to that. We have our fields. We have to use whatever bioresources we have, and we have to compact that, store that decentrally, and then possibly pre-separate decentrally, and then provide energy there, and of course return in order to manage our resources, whatever we don't need, and whatever goes back to the fields and back to the land and back to the water systems. So keep as much as you can close to the site where it is actually generated. And then we can, of course, go on and transport what we have separated here to central units, and then we can process them there. And what you see here is another total site, which is a fully integrated biorefinery that now is not at one site, which is distributed all over the place, all over the region. And we're going to optimize this kind of thing, and we will need all the help we have from process industry knowledge and from process industry methodologies. With that, I want to thank for your attention.
Thank you very much, and we've got Zain with the concluding presentation. We are more or less on time.
Thank you very much. Today I'm going to be talking about something quite different, which is water. In SDEWES, as you notice, water is conspicuous. Conspicuous by its absence, actually, rather than conspicuous by the presence. As you can see, water here is blurred. If in the first place, when Yuri was asking me to talk about be a panel of the total site, the first impression the first thing that came to my mind is to talk about energy, which lately I'm more and more into energy than water. But fortunately, I have chosen to speak about water, and notice that in SDEWES, when we talk about water, it's basically we talk more or emphasize more on the wastewater side rather than the water sustainability or water minimization issues. And so is the case for the policy. Yeah? In the case of policy, not much of the policy or little of the policy covers aspects of water sustainability or water minimization. And for industry in particular, the pain lies in the fact that wastewater must be treated. They got license to operate by treating the wastewater to the level that is required by the authority. So the other thing about the absence of, conspicuously absence of water research, water sustainability research is because water is seen to be cheaper, or probably the cheapest utility, against the fact that basically this is because of the lack of understanding of the nexus or the link between water, energy, environment, and economy. Let me repeat the fact that I have presented the other day. Water shortage is one of the highest global risks in a recent report by World Economic Forum. What does it say further? It affected 4.2 billion people, or 95% of all people affected by all disasters. This caused about $1.3 trillion of damage, or 63% of all damage. You can imagine that. And this is actually talking about water sustainability and water shortage, water crisis, lack of water, rather than wastewater. So what is the cause for this dramatic statement of water shortage giving the largest global risk? Why is it? Why are they saying this? It is because of water usage, on one hand, demanded significant amount of energy. As you can see from the energy, water cycle, from the water sources, at the source of the water, when we convey water, we need a lot of energy to transfer through pumps system. And when we treat water, we need a lot of energy as well. Throughout the whole supply chain of water, concerning the distribution, the usage of water, treatment of wastewater, and discharge of water, we need significant amount of energy. That is the reason why water is closely linked to not only energy, because you use a lot of energy, we tend to also pollute. And also both environmental emissions as well as environmental liquid and gas emissions, and as a result, it affects the economy of a process and a total site in terms of the cost of energy, the cost of purchasing the water, the cost of treating the water through chemicals, and the capital cost of building larger wastewater treatment system and water treatment system. So all this, what we call as a water 3Es nexus, is actually the one that is posing a global risk. But it's not just only that. As you can see, water usage causes liquid as well as environmental discharge, emission discharge, and also as a result, it is also threatening the climate. Climate change, because pollution in the form of liquid as well as gas causes global warming, is the result of global warming, or contribute towards global warming, and it contributes towards all other natural disasters, like for example drought. Global warming causes drought, and changes of weather, flooding for example, and flooding in particular affects the quality of water and access to good quality water through pollution of water. So this is the environment nexus we're talking about. And energy, on the other hand, on the flip side of the coin, the generation of energy demands a lot of water, and it causes water shortage. So it can be on the cycle. And pollution also causes water shortage, because the lack of water, quality water, causes water shortage. At the same time, global warming causes water shortage because of flooding. Flooding threatens the quality of water. Drought also threatens the availability of water. And on the other hand, population increase causes water shortage, as well as demand from industry, and included in the industries, agriculture causes also water shortage. And in the end, it affects the economy. From the previous slide, you can see that this is the reason why World Economic Forum has classified water as the biggest global water, biggest risk. What we call as W3E nexus, water, energy, environment, and economic nexus. So what is the impact that's going to be? If we go business as usual, by 2030, the world's projected to face 40% global water deficit. That's not too long from now, just 15 years. 40% is almost half of the world population is going to have a lack of access to water. So in the end, in summary, water sustainability not only help company comply with regulation and allow them license to operate, it also avoids production disruption or production risks, because lack of water, if you do not have water, you cannot generate power. You cannot even use renewable energy because you do not have cooling system for the renewable energy, for example. And it will also reduce the costs related to purchasing, treatment, and discharge cost of water, and reduce energy costs. And in the end, it will mitigate the significant environmental risks that I posted in the very beginning. So it is vital for water sustainability to be ensured in industrial sites. So water and industrial sustainability is closely linked, and it deserves much higher priority than now, as I see it in SDEWES. Thank you very much for your attention.
Thank you very much. So we finished presentations, and now it's the time for discussion. I hope you are not too tired, but it's after 8. Good time for the dinner, but you are welcome to make statements, comments, questions, suggestions. Yes, please. You will get the microphone.
Okay. My name is Mohammed Khalil, a process engineer from Egypt. The doctor mentioned that power generation reduces water, but sometimes the water is byproduct from combustion of fossil fuels. So if we can capture the greenhouse gases from this fossil fuel combustion product, we can condense the water as a byproduct from this combustion and become a source of water. And instead of, I know we lost water for cooling and the process of power generation, but also the some of combustion product is water. That's my question. Thank
Yeah. It should work. Yeah.
Okay. Yes, water is one of the products of combustion, but CO2 and CO are also products of combustion and much more, a lot more than water in particular. So basically, we do not want to produce water at the expense of polluting the environment through CO2 and CO. I think that is the reason why there is no commercialized process on recovering water. In fact, it can be done, but there is no commercialized process so far on recovering water from the product of combustions.
we can get double benefit by capturing greenhouse gases. At the same time, we can, after we capture this greenhouse gas, we have a water vapor can be condensed without producing some acids due to presence of water and these gases. So we can capture pure water after we capture the greenhouse gas from the product of combustion.
Possibly the one that is being produced in terms of water product is just a very small fraction of water being used in the form of steam.
However,
Thank you.
Okay.
Thank you.
However, this energy-water nexus, it's getting very deep. I don't know if you noticed the sheer scale of desalination to get drinking water. The city of Beijing is going next year to commission a huge desalination plant to provide drinking water. It's about 50,000 tons capacity. And what it means energy, and it needs a lot of energy. And so the relation between water and greenhouse gases and other pollution is becoming more and more obvious. You know, good old times when we had nearby our house the crystal clear stream, and our great grandfathers and mothers came just to take it from the stream, unfortunately over. Another issue is about energy and water. I looked through statistics of US utilities companies, water companies, and 36% of the cost is the bill for energy, for pumping to deliver the customers, and also various pumping for cleaning the water. So, you know, this is something what we will face in the near future very much. I'm not talking about countries in the Gulf where it's obvious that it's needed desalination or something. Okay, yes?
Going back to the condensation, I don't think that it was meant that we should burn fossil fuels to get water. But for existing power plants, condensation is almost a must. Not only for retrieving the water from the moisture, but also retrieving the heat from the latent heat, which is like, in the simplest case, is the condensing boiler. We get, at the same time, some water, instead of going to the atmosphere as a moisture, humidity, but at the same time, we recover a substantial amount of heat from condensation, latent heat. So we have to consider these two nexus, actually they go hand in hand. Thank you.
Okay. Yeah, sure.
I would like to make a comment. There is one commercial actually solution, existing solution for collecting condensed for drinking water, and it is in spaceship. There you have this methane, which is by actually it's another micro system.
100%
yeah, so you get you get C and hydrogen, and then from hydrogen you get some energy, and then after you can drink this water. So this is one possibility.
Okay, to the other comment, who would like to? Yeah.
Well, the condensation, I think the gentleman meant about the condensation of water that recovers significantly the water being used to transfer energy is the condensation of steam. Yeah, that is a closed loop cycle, but still you need to burn some form of fuel to be able to generate the energy required, yeah, by steam. So basically, in the case of what you mentioned, that is true. You can condense, and it's required to condense steam into water so that you can have water back to close the cycle and to produce steam back. Yeah. Yeah, yeah. You need to condense them. You need to condense steam into water. Yeah, it's a closed cycle.
Not a closed cycle.
Sorry?
In a condensing boiler, it's not a closed cycle like in a steam boiler.
I would say that is even worse. If you do not have a closed cycle, that is even worse. You're basically polluting not only the environment through CO2, but you're also polluting the environment through discharge of water.
It's understanding. In a condensing boiler, the flue gas through the chimney. If you condense this flue gas, which is already...
What is the fraction of water? Does anybody know? Can anybody appreciate what is the fraction of water?
As I said, it is little.
Very
but
little.
At the same time, you are
Below
retrieving heat, which adds on about 5 to 6 points of efficiency on a boiler. It's a substantial amount of heat.
Yeah. So,
okay. Yeah.
But the amount, what we're saying that is the amount of energy that you need, yeah, and the amount of CO2 being produced far outweigh the water being recovered from the condensation, which is a small fraction.
Where do you spend the energy? From the flue gas? Do you spend much energy than you retrieve for condensation?
Sorry?
Okay, you can discuss it later. It's fine, but we are coming to one direction, which...
I just want to get the numbers right. I mean, when we talk about water, the largest consumer of water is agriculture, by far. 70%. This is the one thing. The other thing is that if we talk about global warming issues, we should also be aware of the fact that water is the most potent global warming gas in terms of what it really means in the atmosphere. I mean, almost 3/4 of the global warming is because of water.
It's the most...
So, wow. We are talking about 1/4, and we're doing a lot of fuss there in terms of reducing CO2 and things like that, which I support. But on the other hand, what we don't do is that we talk about resource management in water, in agriculture, and we are changing the water cycles by our way of doing agriculture in dramatic ways. So that is another nexus that we have in terms of what we have in terms of bio-resources, how they are linked to water cycles, because of the change in land use and the change in agriculture. So there is a lot of interaction between those basic resources, and that's what we are going to have to manage if we are trying to get into a sustainable pathway.
Thank you. Well, we discussed a lot about the water.
I would like to add something to the point which you have raised for the energy requirement for the desalination. So this is true that few years ago, the energy requirement to run this desalination plant, it was met by the using conventional resources. But at this very stage, I think it is better to make use of renewable energy sources, for example, photovoltaic. Because the cost of the photovoltaic panels, okay, as in today, it has been reduced drastically. You know, if we talk about 10 years ago or 15 years ago, the cost of per kilowatt hour energy produced from the photo, it was very high. But nowadays, with the volume of the panels being produced at high scale, the cost has been reduced drastically. And moreover, I think that this technology, solar power seawater desalination, using reverse technology, reverse pyrolysis technology is the best, and I think this is the best option, and the maximum effort must be made to make use of the photovoltaic technology so far seawater desalination is concerned.
Well, before we pass it, the new technology is something what is making big changes. However, if you need the sheer scale, if you would like to supply Beijing water with solar evaporators, you would probably need to cover a substantial part of China. On the other hand, we've got here nearby Dubrovnik very environmentally friendly historical and traditional production of salt with no extra fossil fuels, just with the sun and with no panels. So I think we should try to learn as much as possible from simple solutions, because to make complicated solutions, a lot of people can do it, but to make it simple and environmentally friendly, this is the real task. Yes, please.
I have one comment first regarding considering water as a greenhouse gas. IPCC is not considering this as a greenhouse gas because it is condensable, and other gases like CO2 are non-condensable. So the condensation with temperature protect it to have an impact on warming. So this should be understood in this way. But my comment is to Professor Narodosławski, not a question, but just a proposal. I think the most difficult thing is to implement the social dimension into these procedures around optimization of biogenic, especially, systems. Could you elaborate on this a little bit?
Okay. Do you have another 2 hours?
We've got 10,
2
15 minutes.
2 minutes. The first thing is, of course, that it is clear that if we are talking about such a system that is as wide as I have described it, this is a system that requires social decision-making. And in the social decision-making, we should clarify where the role of engineers and our role is, and that is a supportive role. It is not that engineers or models or whatever decide. What we can do is that we support social decision-making processes. And there are quite good examples of that, and there are quite good approaches to that. And what I would advise is that we are not going to do that on a very large scale. I mean, going up to our national government and say, I have a good idea for your resource utilization, that is futile. But going down to the regions, going down to urban regional systems, that is much more promising. And there you have social processes in place and social cohesion in place that actually plays a good role in then implementing those things. Because I'm with Sharifa. I mean, what does it actually, what's good in publishing if nobody is reading it? Or not those people are reading it that actually could take some advice of that. So what we have to do as engineers is to involve ourselves in these social processes. And that's not what we are used to do. That's something that we have learned, that we have to learn. And what we have to bring to that is quite valuable, because the methods that we have developed are really supportive of those social interactions and those social decision-making processes. So we could go there with our head up, but we still have to think that the decision is a more participatory decision than just saying we know. There is a difference between them.
Yeah, I very much agree with Michael. It's, you know, it's something what we should learn. The way we had generally two options: revolution or many evolution steps. And if we look in the history, what works much better? And even in the technology, I spent with Petar some time working in the Tyndall Center for Research in Climate Change. And they had about a half of people non-engineers, you know, psychologists and people whom I considered how they can contribute. And I learned similar lesson. We can make marvelous new technology, but somehow we have to persuade people to use it. And governments are usually using brutal force, you know, taxation, or orders even. And this is not the way ahead. To show that it works in a region, it's easy to communicate and much easier to persuade population to do it. And when you can demonstrate it, it's fine. In our total sites, when it's one owner under the fence, it's again not too difficult. You know, this is not by persuading, it's usually by a little bit brutal force. When buyer decides, you know, it's no question about it, but they've got their own responsibility. If it doesn't work, they are in deep trouble. So I think this social part and demonstration and persuading is very, very important. Okay, Stas, you wanted.
Yeah.
So
I have a question, but really you are ahead of my question. So my question was about this, how to teach the policymakers and etc. Because Sharifa mentions this complex problem and it becomes more complex, and how to catch it, and because the education of policymakers is going down and the technology is going up, so how to fit it.
Yeah, we more or less answered it. It's no magic answer. And if you look on many technology steps, sometimes they went through by good luck, sometimes by brutal force, but most of them by step-by-step development. We've got you know, examples like European Commission prohibited to use old-fashioned bulbs, which I consider as an engineer very good. You know, this saves a huge amount of greenhouse gases. But there are people who feel that the human rights are offended. And I don't know how it is in other countries, but in the Czech Republic, they are not selling bulbs, they are selling smaller heaters. But you know, those people are actually who are lighting the houses by very inefficient source of light, they are suffering financially, but probably not too much. And this is actually the question for some future panel discussion, how to persuade people that they should go to the paradise, but without using stick or gun. And I think this is quite a big challenge for the mankind.
Well, I may add to that. First of all, the real way to do that is to engage people. So if you really want, I mean, we have some experience in this regional processes. And the most important thing is that you engage stakeholders in the first place, not when they are already fighting. If they are already fighting over something, keep your fingers off. Huh? But you can engage them if they are really willing to make plans for the future. That's the point when you can intervene. This is the one thing. The other thing, I mean, educating means also educating students, educating our engineering students. And we made quite some successful attempts in that, and we are at the moment generating a new curricula around that. And one of the things is that you get your students out to those stakeholders in practice and allow the students to try to find solutions for their problems. And then also engage them in the discourse with the stakeholders. And that is really good because on the one hand, I mean, you don't have anything as creative as a bunch of 23-year-olds that are partly educated. Huh? That's very creative. This is the one thing. And the other thing is that they learn how to present themselves vis-à-vis stakeholders and what their real problems are and how they quarrel in between them. And that's very important for educating engineers, at least for the future. Oops.
Okay, so yeah, we still got 3 minutes, so.
Okay, it's a very interesting question about how can we help to educate policymakers. In my opinion, there are several ways. One is through media. There are things that people call science writing, is it? Science writing. So I think what we're lacking, science journalism, all right, sorry. So one of the things that I feel that we are lacking is the technique, the capability to write in medias. You know, we are not like newspaper reporters. We know how to write academic journals, but we are quite lacking in how to write in layman, how to talk to people in journals, in media and so on, newspapers and so on. So I think one way is, I think we should all learn maybe how to write in medias, contribute to newspaper, magazines and so on. That will be one way to reach the public, the engineers, like Chemical Engineering magazine is a good source for engineers. Many engineers read Chemical Engineering magazines and so on. So that's one on how to reach engineers on our techniques. The second is training. Aside from education, as has been mentioned, I feel that we should actually make 3 types of training. So in our center, we make 3 types of training. One is the technical training. Technical training is all the techniques that we have met. So we teach engineers on how to use our technique. The second one is management training. So we teach management about how to make decision making, how to make decisions. It's not about technical, it's about management. And the last one is about awareness training. Awareness training is for everyone, the locals. We teach them about water scarcity issues, energy management issues, and so on. So normally in our center, there are 3 ways that we try to communicate our technologies to people, through management training, technical training, as well as awareness training. The other way to approach policymakers is by joining the decision making. So we can always join the blueprint decision making. Like for example, in Malaysia, we have the Academy of Science Malaysia. So the Academy of Science Malaysia, they call the academia and ask them to contribute in the blueprint making of Malaysia's various blueprints. So this is one way we can contribute by joining this blueprint discussion, blueprint makings of state policies country policies and so on. And we should tell them about our opinion. We should tell them about the technologies that we have. We should make them aware. So we should speak up during all these discussions and so on. And maybe instead of the previous scientists, which are more inside labs, only in front of computers, we should start to become someone who can communicate to people, talk to people about ideas and so on. So I think that is something that all of us have to do if we want to make a change to this world. Thank you.
Okay, thank you. I promise to complete this discussion by past. I would like to thank everybody who stayed with us until this time when nightclubs are opening and in Hungary restaurants are closing. Thank all the speakers, and let's consider what next SDEWES we will do, but I will strongly advocate how to persuade people to accept the latest and most advanced technological achievements. Thank you very much.
Special